Okay, so now that we know kind of qualitatively how everything works, we need to put some numbers to this, okay? So for us to do that, we should be talking about, can we find concentrations of all parts of weak acid and bases in solution? And the answer to that question is yes, we can find that, okay? To do that, we just have to go back to two different pieces of information that we already know, okay? First is working with pH and hydrogen ion concentration, so using the pH formula. And the second is using our equilibrium expressions that include hydrogen ion concentration or hydroxide ion concentration in them. So you can imagine that we can use pH to find this number or this number. We can look up Kas and Kbs in tables. So then we're really stuck with, well, how do we find the conjugate base from this and then the original weak acid? Or how do we find the conjugate acid and then the original weak base, okay? One nice thing is when you work with our solutions with acids and bases, if we go back to this, as your acid splits apart, it always makes one hydrogen ion and one anion. So it's always a 1-to-1 ratio. What that means is the number or the concentration of your H plus and your A minus will always be the same, okay? As long as we don't do something like Le Chatelier-wise in terms of stressing the system, which we're not going to, these two numbers should be equal to each other. So if you know one, you know the other one. Same thing for bases. If we know the hydroxide ion concentration from using pH and pOH, that number will equal this number. They will always be the same, okay? Which means as we are solving this, we have two steps we go through, okay? First of all, we're going to use pH or pOH, if that applies, to find the hydrogen ion concentration or hydroxide ion concentration for bases. That's going to equal the conjugate base or the conjugate acid because of those equal molar amounts. We've already talked about that. And then the second thing is we're going to take the value from the H plus, insert that into our equilibrium expression, use our Kas to find the concentration of the non-ionized part of the solution. So the non-ionized part right here, that's this, okay? That is the acid that has dissolved into solution but did not ionize or did not break apart into H pluses and A minuses, okay? That's why we call these weak electrolytes, because some of it doesn't split apart, okay? Now, one caveat is we only can do this math for monoprotic acids, okay? And the reason why that is because every protonation, or every time a hydrogen ion splits apart, it does so at a different ratio in comparison to its conjugate, which means something like H3PO4, all three of those hydrogens that split apart does so at a different ratio from each other. So you can't combine them together into one simple problem where you have three H's here to do it. You had to do it separately. Or you need to use a more complex level of math than we're going to work with in here to find that out, okay? So that's one thing to keep in mind, that we only will do one acid, one protonation at a time as we do these, okay? All right, so let's do this little practice problem with it. So here's our problem. We have an unknown concentration of hydrofluoric acid in solution. So someone made some hydrofluoric acid up, didn't measure this concentration. We have no idea what it is. But we test the pH to be 3.25. So what we want to solve for is the concentration of the hydrogen ions and the non-ionized acid at that equilibrium, okay? So let's write down what we know and let's solve this thing. So we know that the pH is 3.25. We can look up the Ka for hydrofluoric acid. In this case, it's 7.4 times 10 to the negative 4. And then we want to write our equilibrium expression because we're going to need that also. So the Ka for hydrofluoric acid. Now, hydrofluoric acid, let's move that down a little bit. Hydrofluoric acid, HF, is going to react to make hydrogen ions and fluorine minus ions, okay? So like normal equilibrium expressions, we're going to put our products over our reactants. So we're going to have our hydrogen ion concentration times our fluorine concentration over our HF concentration, okay? Now we need to start to plug some numbers in. Though with pH, we can find the H plus concentration because we know that H plus concentration is equal to 10 to the negative pH, okay? So we're going to solve for that. So let's do that first. And if I take 10 raised to the negative 3.25, if I do that, I get an H plus concentration of 5.62 times 10 to negative 4 molarity. So that's the first part of our problem. We've already solved for the H plus concentration. Now that I know that, this value is this number and this number, okay? So it's both of those. I know my Ka is this value, so the last thing is to solve for my HF, okay? Or what is my non-ionized acid in this, okay? So to do that, I can plug my numbers in, rearrange, and solve. So rearranging this thing, I am going to say that my HF concentration should equal my 5.62 times 10 to negative 4. That is going to be twice. You could put it squared if you want to. Not twice, actually, it's squared here. Times 10 to the negative 4. All over the Ka, which was 7.4 times 10 to the negative 4. Okay? If you don't want to write these twice, you would have to do 5.62 times 10 to the negative 4, and you would square that value. Okay? Don't take it times 2. That's a common mistake students make in this. And then plug into your calculator, and we solve it. And if we do that, we should come up with 4.27 times 10 to the negative 4th molarity. Remember, concentrations are molarity, so we label it molarity. Okay? So really, all we're doing in this practice problem is taking things that we've already learned how to do and using it to our advantage in acid-base chemistry. So we know how to use pH to get this. We know what equilibrium expressions are. We know how to solve with equilibrium expressions. We just need to apply the acid concept to this thing we already know how to do. Okay? And that solves for this. Now, obviously, we could flip this around. We could, if you didn't know the Ka and you knew this, you could solve for other things. But just like any of our math stuff, we can sometimes give you different information and make you solve a different part of it. Okay? How about for a base? Can we do the same thing for a base? Absolutely, we can do the same thing for a base. Set up the same way, solve it the same way, work it out the same way. The trick for a base is realizing pH is going to give you H plus concentration, and you need to get hydroxide ion concentration here too. Okay? So let's do this one for our base here. All right, we're dealing with aniline is our base, and we know that our pH is 8.65. So I'm going to change that to a POH by subtracting from 14. So 14 minus 8.65, and so my POH is 5.35. So I'm just going to do that ahead of time. Okay? We're looking at aniline, and aniline is down here, and we have a Kb value for aniline, 7.4 times 10 to the negative 10 now. I'm going to write up my equilibrium expression, my Kb. Here's my equation. Whoops. Well, I already did that part for us, I guess. Here's my expression. So Kb is going to equal to my C6H5NH3. That's the conjugate acid with a positive charge on it, times my hydroxide. And water here is not going to be included because it's a liquid. And then the base is the C6H5NH2 here, concentration. So here's our equilibrium expression. All right. And then, like we see on the screen here, the first thing that we're going to do is take 14 minus 8.65 to get our POH. Take that to the 10 to the negative 5.35 power to find the hydroxide ion concentration. Okay, so now that we know the hydroxide ion concentration is 4.47 times 10 to negative 6 molarity, this value again is both this number and this number in the equation. The Kb we know, so let's solve for our non-ionized aniline in here. Okay, so same deal, rearrange the equation, and if we do that, we can see, take a look, here's our equation. We've rearranged it, we put those in twice, we divided by the actual Kb value now, or the equilibrium constant for a base. That's why we call it Kb. And we should get 2.7 times 10 to the negative 2 molarity at equilibrium. Okay. All right, those are a couple of practice problems. If you need more for this, you can find some in your student files worksheet on this. Thank you.